Let's talk about clock domains, metastability, and synchronizers. A big thanks to all my supporters, especially those of you that have gone that extra mile listed here are the VIP patrons. If you want to be a patron of this channel, feel free to follow the link below. There's a link in the description below on YouTube as well if you want to click on something. The Wikipedia page does a pretty good job here. There's other papers and things, like here's one from Altera. I mean, I'll show you the main things here. If you Google it around, you're going to see a lot of copies of this drawing here, and we'll come back to this a little bit later. And this drawing in here with this little squiggle in there. You can see that's the same one you've got on Wikipedia here as well, okay? So this is pretty much the standard description here. If you don't like mine, I'll put a link below to a lecture on MIT that takes a little different slant than I'm going to take on describing this as well. So one way or another, you can get this covered. And you really, really, really want to know and fully understand, I mean, grasp this internally if you're going to write FPGA code that has any kind of external inputs into the FPGA as part of your circuit. This is a big deal. All right, so let's make sure that we all got it before we start moving forward and start questioning how come my circuit doesn't work. All right, okay. And this, of course, addresses a what is commonly known as a heisenbug. By the way, let me do a Google search on that. Well, in programming jargon, it's a software bug that it seems to disappear or alter its behavior when one attempts to study it, okay? So once you observe it, you change the system, kind of a thing. These things, when they creep up in your circuitry, cause a lot of trouble, okay? So let's start with what is a clock domain, because that's where these kind of come in. So let's have a look-see at this diagram here. There'll be a link to this Wikipedia page below on the YouTube description box, so you can find it yourself if you can't Google it. Anyway, what we have here is a diagram from a 10,000-foot view. Ignore everything down here. You see where it says clock A, clock B. You see how they have flip-flops over here and flip-flop over there. This design has two clock domains in it. By that I mean this clock here may run at a different frequency or at a different phase from the clock over here, clock B. Every one of the flip-flops that are connected up to clock B are in a domain. This is the clock B domain over here. This is the clock A domain. And it's when a signal crosses two domains that we are caring about what I'm talking about today. That is it, okay? Some data here changes as a result to an edge on clock A, okay? I mean, clearly, no matter what's happening over here, you could easily say that if Q here changes for any reason, then it changes at the time there's a leading edge on clock A. Or more accurately, within the propagation delay time of this flip-flop after clock A's leading edge, okay? At which point, this Q can change its value from 1 to 0 or 0 to 1. And that is in complete independence of what might be happening in the circuit over here that can only change when there's a leading edge, as drawn here, on clock B, okay? And like I said earlier, if clock A and clock B are not the same frequency and the same phase, and I mean, in other words, if they're not the exact same signal, then you can have a problem, because you could violate what we already know, commonly referred to as the setup and hold time on this flip-flop over here. And it goes beyond the problem where if this is a 1 over here and you got a leading edge and you miss the setup time, maybe this output is still a 0. That's not what I'm talking about, okay? Now here's where the metastability comes in. You understand we got the two clock domains. If you do not meet your setup and hold time on D in around the leading edge on clock B, you don't really know what's going to happen over here on Q. It could be a 1, it could be a 0, or it could be metastable. And that is a big problem. If If you go see the MIT lecture, they talk about the FETs and the totem pole driver inside this D flip-flop, and that depending on what happens, depending on the way this thing is designed, you can have both the up and the down pulling FET on at the same time, which represents a direct short across your power supply. That's a real bad case of the metastabilities. All right, so this is not something you want to have happen. You could physically destroy the circuit if it is a self-destructive design, okay, all because you miss your setup and hold time. The other problem is a bit more subtle. And it's in, that's a different, this is a different kind of metastability, by the way. In chemistry, there's different types. I wanted to make sure I reminded myself by leaving this in here to mention that if you start reading about chemistry and states between chemical reactions, well, that's the wrong one. You want to read the one about this ass is a whole nother story. We'll come back to this in a minute. Let's run with our metastability state over here on D sub S. So what happens here, if this clock A and B fire and you don't meet the setup and hold time, if D in over here is changing too close to around the same time the clock B rises, this can have a problem. And it literally won't be a, well, it doesn't matter, it'll still be a 1 or 0 kind of reasoning. No, that's not what happens. The voltage, this thing can start operating in a linear amplifier kind of a mode and not be either 1 nor 0 and end up quivering around in the middle, which is a big problem. That's what can cause FETs to go into a nutbag state and cause, high current drain inside the chip. This can be very bad. And let's bring back our little Altera drawing. See this hill here? This is the diagram of probability, right? If you put a ball on top of a hill like this, you would argue it'll go one way or the other way. But if you put it perfectly in the center, it could be balanced up there and stay there an arbitrarily long time, and this is the big problem. I'd stand up and wave my arms around if I was on camera right now, but I'm not, so I won't. That could stay on there forever if you balance it perfectly. Now, normally it won't, but it could take a long time before it starts to move. A breeze enters the room, or a cosmic ray comes nearby, or an electric field collapses from a coil across the circuit board. Something could cause a little something to change, cause this to quiver and wander down one way or the other. Okay, this is your problem. If you have the output of a flip-flop that can't decide because its input saw a changing edge too close to the setup time, hold time on your clock in the domain in which your gate exists, this flip-flop over here, you're going to end up with something that goes like that. And it could take a long time for that to happen, okay? Now, normally it doesn't take a long time. It's a probability thing. In theory, it could take an infinite amount of time if it's all just right. So, you don't violate your setup and hold times. Then this can't happen, by the way. But, if you're dealing with an external circuit over here and you don't control the phase relationship or the frequency of clock A and clock B, you can have this problem, and you need to know how to deal with it. So, that's a clock domain. That's metastability. This is what causes it. What do we do about it? And this is it right here. End of lecture, just put 2 gates in there, all right? Well, yes and no, okay? Look and see what happens here. If you have a violation of your setup and hold time over here, and you have your rising edge here, and it quivers around a little bit in there, there's a very strong case to be made that if this is not running very fast, and not very fast means like under 100 megahertz, maybe even faster than that, maybe under a couple of 100 megahertz, this is going to stabilize, okay? It's when you're going super duper 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 fast where this may not stabilize in time for this other gate to get triggered and go through. Look what's happening here. We got a shift register. Okay? When this clock, let's say Q is 0 and DS and D out, I should say, let's say they're both 0 right now. And let's say D in is a 1. And it is a 1 from an hour and a half ago. So you met your setup time. Let's say we have a rising edge on clock B, and DN stays a 1 for 10 minutes afterwards, so we met our hold time. What will happen is that DS will go from a 0 to a 1 in that scenario. And D out will still be 0 because when this thing had its rising edge, DS over here was a 0. That 0 will be clocked out of there. At the same time, we can say that D in, which is a 1, gets clocked over to DS. So what happens is you got a 1 that goes into here and a 0 that goes over to here. The next time clock B rises, let's say DN is still a 1, then DS will stay a 1, and this time D out will become 1. Okay, so this is a shift register or a delay of 2. Okay, you got to wait for 2 clocks to go by before this signal shows up over here. Okay, it's a pipeline. Okay, think of it as, depending on the context that we're talking about, you can call this, refer to this in different ways. All right, but basically it's causing a delay. Now, let's say we violate the setup time or our hold time, and you end up with this situation over here on DS. And let's say that this clock B here is not running all that fast, right? Under 100 megahertz, under 200 megahertz. Odds are the circuitry in here will stabilize before the next leading edge on clock B. And that's why if you put a delay in here like this, if this does go metastable, statistically speaking, it's probably going to settle down by the time the second clock comes along, and you'll have a scenario like this. Okay? If DN is low and you're clocking away over here in clock B, all these stay 0, just like you got over here. Okay? DN goes 1 at a bad time. DS quivers around a little bit, but he's still 0 because at this leading edge, this was 0, so 0 is clocked out of there, right? Next leading edge, by then we hope this stabilizes early enough to meet the setup time on this second leading edge on clock B over there, at which time you transfer DS over to D out in a clean edge. Okay? If this doesn't happen, or you're running it too fast, or you're concerned that this could continue, you can have metastability over here on D out as well. What do you do then? Well, you can add another flip-flop over here and put a triple jobber in here. The odds of that, it's like an exponential probability decay. You know, the more you put in here, the odds of it propagating all the way through all of them over that many clock edges is really close to 0. It never becomes absolutely 0 because of this over here. In theory, that ball could stay on the top of that hill forever. And that's a bit of a drag. And there's really nothing we can do about it. You know, as FPGA, designers, HDL programmers, this is just one of those things we have to say, well, it's unlikely to happen. Unlikely, and 1 in a trillion. But that's, only 1,000 clock cycles at a gigahertz. So how long does that take, right? Oh, my gosh. Or rather, what am I saying? It's 1,000 seconds, I should say, of a signal running at a gigahertz, okay? And that's only, 15, 16 minutes. So you could end up in a situation where you've got a metastable signal like this propagating out of this here, which we refer to as a synchronizer, okay, and propagating into the rest of your circuitry inside your FPGA. And then the whole circuit in here could become metastable. This is a viral infection that can run through your design, okay? So you want to make sure you think about it when you're bringing in a signal that can change at a time where you cannot predict. It could be random with regard to the clock that drives the domain in which it's being received, okay? You've got to be very careful about this. You got to understand when this could happen and what do we want to do about it. Pretty much if you put two together like this and you're running under 100 megahertz, I don't really concern myself that much about it. If you're going faster than that, or you've got some other other circumstances, you might need to put another flip-flop in here, okay? Now, notice they say here's your combinational logic over here. You got combo logic. Whatever you got over here in this clock domain, however this is created, doesn't matter. You've got a signal that can happen asynchronously to clock B, and that's the scenario they're talking about in here. Now, I mentioned this combinational logic over here because there is no combinational logic here. And this is relatively important, because if we start thinking about, what could cause this to propagate from this flip-flop over to this one here. Well, one of the answers that you could cause this to continue through here and infect downstream of the output of this flip-flop is if DS takes a long time to go from Q to D. How do you slow down this thing, right? You put combinational logic in there. You got to deal with propagation delay through all your gates, or in this case, it would be through the LUTs and routing fabric inside your FPGA. If you connect a flip-flop directly to another flip-flop, odds are the floor planner and the compiler, when you build your code, will put these things physically close together inside the FPGA, because they're directly connected, and it's only this signal here would normally not be used anywhere else in the FPGA. Therefore, it would try to minimize the length of this net. Okay? And even if it was relatively long inside your FPGA, that's still better than actually putting LUTs and stuff in here and creating combinational logic between this flip-flop and that flip-flop. So do not put this into any logic, okay? You need the minimum propagation delay between this flip-flop and that flip-flop in order to maximize the odds that any quivering around, any metastable noise that eventually settles out in this flip-flop will have done so in enough time to meet this setup for this edge over here when clock B next rises, okay? So I wanted to make sure I point that out as well. This is not just free reign to put anything you want in here. You've got to hook these up back to back, literally build a shift register. If your clocks are too fast, you might have to put 3 or 4 of them in here to guarantee you don't have this getting all the way through. Okay, so there's your synchronizer, and that's the whole ball game. We could stop talking right here and now. But let's ask ourselves, do we always need this, right? How do I know? It may not be obvious to, if you're just getting started on all this stuff. When do I really need to do this? When do I not need to do it? Well, let's do a search for SPI protocol. I submit, if you have an SPI device and you want an input, you don't need a synchronizer. And the reason is, SPI, if you look at this design down here, once you pick your mode and your phase, it has mandatory setup and hold times. Now, we get into the argument, the principle of, yeah, but what if it does violate its setup and hold time? Well, the answer there becomes, how much can you compensate for the ineptitudes of the circuitry outside of your FPGA? Now, if this was a life support system, you may want to put a little more effort into this. If this was a hobby situation and you just want to hook up an SD card or something like that, you can probably trust that you'll be okay, because if you get a 1-bit error in here, you're not going to die. All right? Maybe your program may not work right, but if you put in the CRC check on your SPI protocol for an SD card, which you should do, you'll detect that error and you can retry the transfer. Okay, so it really boils down to how important it is to get it right on first time every time. Now, a quick review of SPI. What happens is you've got a clock, and it can either be positive or negative polarity. So this is 2 options for your clock that drives the SD device. You got a chip select line, and then you've got your master out and your master in signals, and they either change on this edge here, or they change on this edge here. You know, it depends on what mode and phase, in this case the phase, does it change, you know, right away, or does it change on the other, you know. Let's ignore pole 1, because it's hard to talk about all of these at the same time, because all the edges are opposite. I can't talk about rising and falling edges. So the red edges, which are rising on polarity 0, if we're operating in that mode, okay, every rising edge is when you're supposed to sample, and when the SD card is supposed to sample the data on the data lines, period. The rule is you must not change your data except for on these blue lines when you're in polarity 0. On the falling edge is when the data is free to change, because that's when no one is looking. So if you use polarity 0 and you got these rising edges here, and you're looking at phase 0, then you have, by definition, a guaranteed setup and hold. You're sampling in the middle of the time period where the data bus is supposed to be stable. I don't bother using synchronizers if I properly configure my SPI bus and I talk to an SD card, because the protocol states that it will operate you're sharing the same clock domain, because I'm in charge of the clock, in other words, right? So I don't have to worry about it, provided that I don't accidentally run it in phase 1. You know, if I don't build the hardware right, well, then all bets are off too, right? So this is a situation where you don't need to put a synchronizer in here. You could, but it wouldn't do you a whole lot of good, because the setup and hold times are based on the clock domain that generates this thing. And if it comes out of your FPGA, you can generate this out of this, you know, part of the same clock that runs the internal frequencies inside your FPGA, and keep your internal logic locked in phase with this clock signal that goes out to control the SD card. So in this scenario, the S clock may not be the same frequency of the clock that runs your FPGA, but if it's derived from the same clock signal, you know, you might divide it by some number, because your FPGA might be running at 100 megahertz and your SD card might be running at 10, or, you know, whatever, 20 or 25 or whatever you want to do there. And therefore, if it's derived from the master clock on the FPGA, it will be in phase and locked in phase with the clock that runs inside the FPGA. So you can know that when this edge happens, you can design the logic inside your FPGA so that you're not trying to latch on around these blue periods over here. Okay, so there's an example where you don't need a synchronizer. On the other hand, let's have a look-see at a I2C interface. In an I2C interface, the clock can be stretched. I don't know how much we want to do a review of I2C. Is there a Wikipedia page? I don't want to violate any copyrights, you know. What happens here is that the data line, where's the synchronization logic? The clock and the data, way to call an audible, John. Okay, give me a diagram. Here we go. So what happens here is the data is allowed to change when the clock is low, but it's supposed to be stable when the clock is high. So I would probably monitor it on this falling edge, or odds are the clock line is derived from an internal FPGA clock when you're driving it, and you can easily count out and sample in the middle of the high period of the signal in here, okay? So that's fine and dandy. However, remember that the device can pull on this clock line and make the controller wait. So this clock is not always moving when you control it, when you're the controller, because the device can hold it down and keep it down to stop the controller from going super fast if it's going too fast. All right, so this one may require a synchronizer because you have to be able to drive the clock and look at it at the same time. And if it moves at a weird time, you may have a problem. So you might want to put a synchronizer on the input logic when you're monitoring the clock in an I2C interface, okay? I don't want to get too much into I2C, but this to me is a great example of one of each. This one specified lockstep. This will run at the frequency and in phase of the control unit that drives the clock, period. Okay, so I can count on this protocol doing what it's supposed to do. If it doesn't, it's broken by design, and the repercussions can be problematic, to say the least, if it doesn't do what it says it's going to do. That's just a fact of engineering, right? Okay, so what about the ass? This is ass, okay? So what happens is, this is okay, so in philosophy, right? So you end up with these guys that came up with this concept that says, we're an ass donkey, right? I like to be able to, use dirty words on my YouTube channel. So let's say you got a donkey. And the idea is it's equally thirsty and hungry. And you give it midway between a snack of hay and a bucket of water. What's it going to do? Well, it can't decide. Is it going to eat or drink? Eat or drink? Eat or drink? And they're both, maybe far away. You can see them both. And he basically starves and dehydrates to death because he's paralyzed, right? And they talk about a common variant where there's two hay bales equally distant. Which one does he choose? He can't decide. He dies of starvation. And there's a political cartoon, I don't know, circa 1900, where the U.S. was trying to decide whether they were going to dig a canal through Panama or Nicaragua. And I wasn't alive, of course, back then, although these days I feel like I've been around that long. The joke here was that the U.S. Congress was stuck like, what is it, Buridan? This is probably French. I'm saying it's so wrong. Belladon? I don't know. Somebody correct me. Anyway, this is an example in philosophy of the same idea, where you get stuck, you're in between a rock and a hard place, you don't know what to do. Which way are you gonna go? All right, so I'll put links to all this stuff in the description below, so we can all keep in sync on, no pun intended there, on this entire concept. Because as we design interfaces that bring in data into an FPGA design, an HDL design that runs an FPGA, I should say, you've got to deal with this potential problem in some way. It only affects inputs, obviously. It can't affect an output. If you could generate an output that could cause someone else a metastability problem, but it's not going to affect output data from your FPGA, but it'll affect input data coming into the FPGA if and when the input data could decide to change outside of your control in a way that would violate the setup and hold time of a latch in your FPGA. So this is one of those things that is wonderful. Takes longer to learn what it is and how you got to deal with it than it'll ever take to write the code to create two latches that are hooked together in your same clock that drives the rest of the circuitry over here, and just stick it in your design. How often do things go in your favor that way, huh? Well, I hope all this makes sense. Thanks for watching. I'll see you next time. We might actually apply this to something, like a PS2 interface. Till then, I'll see you on the internet.